In February of 2017, in a paper in the journal Nature, an astronomer at the University of Liège in Belgium named Michaël Gillon and his collaborators announced the discovery of a planetary system that, for a brief period in the mid-2010s, became the most famous exoplanet system in popular culture. 7 planets, all roughly the size of Earth, orbiting a small dim red star 40 light-years from Earth in the constellation Aquarius. The system was named after the small Belgian-built telescope that first detected the planets, TRAPPIST. The 4th planet in the system is called TRAPPIST-1e. It is, by every measurement we have today, the planet most like Earth that we have ever found. Slightly smaller than Earth in radius, slightly less massive than Earth in mass, receiving an amount of starlight from its host star almost exactly equal to what Earth receives from the Sun, sitting in the part of its star's neighbourhood where, given the right atmosphere, an ocean of liquid water could exist on its surface, tidally locked, almost certainly, with one side permanently facing the star and the other permanently facing away, bathed all the time in a dim red glow that no human eye has ever seen. But here is what almost nobody outside exoplanet astronomy is sitting with. The status of TRAPPIST-1e as our best candidate for another Earth is, in part, a function of how few candidates we have. The fact that this small, dim world, with its permanent twilight and its red sky and its strange atmospheric chemistry, is the best we have, is itself a measurement of how genuinely rare Earth-like worlds appear to be in our local cosmic neighbourhood. If TRAPPIST-1e is our best chance, then either we are going to find something better in the next 20 years, or we are not. Either way, the question of how Earth-like the most Earth-like other planet really is one of the more important open questions in modern astronomy. If you find that as fascinating as I do, hit subscribe, pour yourself something warm, get comfortable, and settle in. Because tonight we are going to walk slowly through the strange and quietly beautiful story of a world 40 light-years away, of how we found it, of why it is the best chance we have, and of what its quiet existence tells us about how rare our own home really is. Now let's ease into it. Part 1. The little red star nobody noticed, the host star of the TRAPPIST-1 system, is, by almost every measure, an astronomically uninteresting object. It is a small, cool, dim red dwarf of the spectral type known as M8V, which sits near the boundary between stars and brown dwarfs in the classification scheme that astronomers use. It has a mass of about 9% of our own Sun's mass. It has a radius of about 12% of the Sun's radius. It has, on the most current measurements, a surface temperature of about 2,550 degrees Celsius, which is just over half the temperature of our own Sun. The star is so dim that, from Earth, it has a magnitude of about 18.5. To put that in context, the faintest stars you can see with the naked eye on a dark night have a magnitude of about 6. Each magnitude on the astronomical scale is about 2.5 times fainter than the one before. TRAPPIST-1 is more than 1,000,000 times fainter than the dimmest stars you can see without help. To find it, even with a small backyard telescope, you would need careful coordinates, dark skies, and patience. Most amateur astronomers, looking up at the sky on any given night, walk right past it. The star, despite being one of the closer stars to our own, has been beneath the threshold of casual notice for the entire history of human stargazing. There is a small piece of stellar physics worth pausing on because it explains why TRAPPIST-1 stayed in catalogues for nearly a century without anybody paying much attention. Stars at the very low end of the main sequence, which is the technical name for the long, stable phase of stellar life when stars are fusing hydrogen in their cores, are intrinsically dim. The luminosity of a star scales roughly as the fourth power of its mass. A star with 1/10 of the Sun's mass produces about 10,000 times less light. A star with TRAPPIST-1's exact mass, about 9% of the Sun, is even dimmer than that. The total light output of TRAPPIST-1 is about 5,000ths of the Sun's. To detect it from Earth, even at 40 light-years, you need careful equipment and sensitive detectors. To study it in any detail, you need much more. For most of the 20th century, the star was, in catalogues, simply a number. It had been listed in various stellar catalogues since the 1920s, when it was first picked up in deep photographic surveys of the sky. Its parallax, the small annual shift in its position on the sky due to Earth's orbital motion, gave a distance of about 40 light-years. That was, by the standards of the time, useful information for stellar statistics, but not particularly remarkable. It was just one of many thousands of small, dim red stars in the local neighbourhood. Nothing about it in any survey conducted before the 2010s suggested that anything interesting was happening around it. The thing that changed in the 2010s was that astronomers started looking very carefully for transits around small dim stars. The reason was geometric. When you look for planets by the transit method, the depth of the dimming you measure depends on the ratio of the planet's size to the star's size. For an Earth-sized planet around a Sun-like star, the transit dip is about 1 part in 10,000. Very hard to detect. For an Earth-sized planet around a small red dwarf like TRAPPIST-1, the transit dip can be 1% or more, easy to detect, even with modest equipment. The small dim red stars that in earlier eras had been ignored became, in the modern era, the easiest places to find Earth-sized worlds. That insight, which had been understood theoretically since the 1990s, became practical in the late 2010s. Several groups in different countries started building dedicated survey programs that pointed small telescopes at lists of nearby small red dwarfs and watched for transits. One of those programs was the TRAPPIST survey, led by Michaël Gillon and his colleagues at the University of Liège. The survey used 2 small robotic telescopes, one in the Atacama Desert in Chile called TRAPPIST South and one in the Atlas Mountains of Morocco called TRAPPIST North. Each telescope was a 60-centimetre instrument, modest by professional standards but well suited for the kind of high-precision photometry that transits require. The telescopes scanned a list of about 60 nearby ultra-cool dwarfs, watching each one for periodic dimming events. There is a small piece of context that is worth adding here because it tells you something about how this kind of work actually gets done. The TRAPPIST telescope project was, by the standards of professional astronomy, deeply modest. The 2 telescopes were 60-centimetre robotic instruments, the kind of equipment that, in the budget terms of major space missions, costs less than a single instrument component on a flagship satellite. The team behind the project was small. The University of Liège, while a respectable institution, was not one of the global powerhouses of exoplanet astronomy. The funding came from a combination of Belgian research grants, European Research Council awards, and contributions from collaborating institutions. Nothing about the operation in 2015 suggested that it was about to make one of the most consequential discoveries of the decade. That is, in many ways, the deepest pattern of modern astronomy. The big discoveries do not always come from the big institutions. They come often from small teams using cleverly chosen targets and well-understood techniques to look at parts of the sky that the bigger surveys have ignored. The TRAPPIST-1 discovery is, in this respect, similar to the K2 mission's discovery of K2-18b or to the original SuperWASP discovery of WASP-12b. Modest equipment, well targeted, can find things that the most expensive instruments miss, simply because the modest equipment is being pointed at the right places at the right times. In 2015, the TRAPPIST South Telescope picked up a series of transit events on the small red dwarf that we now call TRAPPIST-1. The events were repeating, with periods that suggested multiple planets. Several of the dips were too deep and too sharp-edged to be anything other than transits of small worlds. The team began intensive follow-up. By 2016, the data was strong enough to publish. The team announced in May of that year the discovery of 3 transiting planets around TRAPPIST-1. The announcement was, in the small community of exoplanet researchers, treated as significant. 3 Earth-sized planets, all in tight, close-in orbits around a single small red dwarf, was an unusual configuration. Subsequent follow-up, using the Spitzer Space Telescope and several ground-based observatories, would over the next several months reveal that the 3 were not the whole picture. There were more. By February of 2017, when the full Nature paper came out, the Gillon team had identified 7 planets in total, all roughly Earth-sized, all in tight, close-in orbits, all around a single small dim red star that, until 2 years earlier, nobody had paid any attention to. The world's press, when the announcement was made, paid attention. The Nature paper itself in February 2017 was authored by a large international collaboration. The lead author, Michaël Gillon, had assembled the team over years of patient work. Co-authors came from institutions in Belgium, Switzerland, the United States, the United Kingdom, Morocco, and several other countries. The collaboration represented, in some sense, the modern reality of exoplanet astronomy. No single institution can do the work alone. Every major result is, by necessity, an international effort, with contributions from many groups and many countries. The TRAPPIST-1 system in its public moment was the product of this kind of broad collaboration. The system, briefly, was on the cover of Nature. It was on the front pages of major newspapers. NASA produced a stylized travel poster of the system in the style of 1930s railway posters that hung on dorm room walls for years afterwards. The 7 planets of TRAPPIST-1 in the popular imagination became a kind of shorthand for what was possible in the new era of exoplanet astronomy. 7 Earth-sized worlds in one system, within reach of detailed atmospheric study with current and next-generation instruments. The first realistic place to look for biosignatures on multiple planets at once. That, more or less, is where this story begins. With 7 planets, around one small star, 40 light-years from Earth, in a constellation that, until 2017, was not particularly famous in popular astronomy. Part 2. The first 3. To understand the discovery of TRAPPIST-1e specifically, you have to understand how the system was unpacked over time. The 3-planet announcement of 2016 was the seed. The 7-planet announcement of 2017 was the full bloom. The journey between the 2 was a sustained program of follow-up observations that, over about 8 months, took the system from a tentative early result to one of the most thoroughly characterized exoplanet systems in the catalogue. The first three planets, designated B, C, and D in order of increasing distance from the star, were all very close in. Planet B had an orbital period of about a day and a half. Planet C, 2.5 days. Planet D, on the original announcement, was thought to have a period of about 18 days. But this turned out, on later analysis, to be wrong. The actual orbital period of TRAPPIST-1e is closer to 4 days. The original misidentification was due to limited transit coverage and the difficulty of disambiguating multiple planet signals in early data. That kind of correction is, in this field, normal. Early discovery papers often have 1 or 2 parameters that subsequent observations refine. The community absorbs the corrections and the system as a whole becomes better characterized. The original 3-planet TRAPPIST-1 paper, in retrospect, slightly underdescribed the system, but the basic claim of multiple Earth-sized planets around a small red dwarf was correct. And it was that claim, more than any of the specific parameters, that motivated the intensive follow-up. There is a small detail about the original 3-planet announcement that often gets lost, which is that the team was, at the time of publication, fairly sure that the system contained more planets than they had yet confirmed. The transit data, looking carefully, hinted at additional periodic signals beyond the 3 they had isolated. The team chose to publish the 3 confirmed candidates rather than wait for the full picture, partly because the publication timing was driven by the journal's review schedule and partly because 3 Earth-sized planets in a single system was, in itself, a result worth getting into the literature quickly. The decision to publish what they had, rather than wait for everything, is a common one in this field. Subsequent observations almost always refine the picture, and waiting for completeness can mean waiting a long time. The intensive follow-up came in late 2016 when the Gillon team requested and received observing time on the Spitzer Space Telescope, NASA's mid-infrared space observatory. Spitzer was, by 2016, in the late stages of its mission. It had been launched in 2003, originally with a primary cryogenic phase that lasted until 2009, after which the warm extension phase used the instruments that did not require active cooling. By 2016, Spitzer was operating in a heavily reduced mode, but its photometric capability was still excellent for transit observations of bright targets. TRAPPIST-1, as a system of interest, was elevated to high priority. Spitzer's role in the TRAPPIST-1 story is, in retrospect, one of the more important pieces of late mission science the telescope did. Spitzer was not designed for exoplanet photometry. It was designed in the 1990s as a general-purpose mid-infrared observatory with science cases ranging from star formation to galactic structure. The fact that it turned out to be also extraordinarily good at the kind of high-precision photometry that exoplanet transits require was a happy accident of its design. By the time Spitzer was used for TRAPPIST-1, the telescope was in the very late stages of its mission. The cryogen had run out years earlier. Most of its original instruments were no longer functional. What remained in 2016 was a single instrument operating at a single wavelength, doing the kind of careful, repetitive photometry that the original designers had not specifically anticipated. The mission in its second life found a niche that turned out to be more scientifically productive than almost anybody had expected. The Spitzer observations covered TRAPPIST-1 essentially continuously for about 3 weeks in September and October of 2016. The data, when it came down, revealed transit events that the original ground-based observations had missed. Some of the events were of planets that had not been previously detected. Some were of planets at orbital periods that the original analysis had got wrong. Over the course of those 3 weeks of continuous observation, the Spitzer program revealed the full structure of the system. 7 transits, repeating on different periods, fitted to 7 separate planetary signals. There is something almost ordinary about how this kind of result actually arrives at a research team. The team had been observing the system for months. The data was being processed continuously in the lab. On a particular day in the autumn of 2016, the most recent batch of Spitzer photometry came down, and somebody on the team, looking at the light curve, saw a transit dip that had not been on the schedule for any of the previously known planets. They flagged it. They ran the analysis. The dip was real. Over the following weeks, more dips appeared on different periods, and the picture filled in. 7 planets. The team, in a certain sense, did not discover the 7 planets in any single moment. The 7 planets emerged gradually from the data over a period of weeks as the analysis pipelines did their work. The discovery, in retrospect, was a process, not an event. The team labelled them in order of increasing distance from the star. Planet B at 1.5 days, Planet C at 2.5 days, Planet D at 4 days, Planet E at 6 days, Planet F at 9 days, Planet G at 12 days, Planet H at 18 days. Together, the 7 planets formed a tightly packed inner system, all closer to their star than Mercury is to our Sun, with the outermost planet H having an orbit that takes about half the time of Mercury's 88-day year. The team also, by careful analysis of the transit timing variations, was able to extract preliminary mass estimates for several of the planets. Transit timing variations, or TTVs, occur when planets in the same system gravitationally perturb each other's orbits. The perturbations cause the transit times to shift very slightly from the schedule that a strictly periodic orbit would predict. By measuring the shifts, you can infer the masses of the perturbing planets. The technique was developed in the early 2010s by several groups, including a team led by Eric Agel at the University of Washington, who would later go on to publish refined mass measurements of the TRAPPIST-1 system in 2021. There is something almost philosophical about transit timing variations as a measurement technique, which is that they require the universe to be patient with you. You cannot, with TTVs, measure planetary masses in a single night. You have to watch transits over many cycles, build up a baseline, look for the small deviations from a strictly periodic schedule, and slowly extract the perturbing masses from the pattern of those deviations. The TRAPPIST-1 system, with its tightly packed planets and its strong mutual perturbations, is in some ways an ideal target for the technique because the deviations are large and the patterns are clean. But even on this favourable target, the measurement requires years of accumulated data. The Agel 2021 paper, which gave the most precise TRAPPIST-1 mass measurements, used data from 2009 through 2020. 11 years of patient transit timing on a single system by a network of telescopes in many countries finally produced the precision we now have. The early TTV measurements, when combined with the radii from the transit depths, gave preliminary densities for the TRAPPIST-1 planets. The densities, when worked out, were broadly consistent with rocky worlds, of compositions roughly similar to Earth. The planets were not gas giants, they were not water worlds. They were small, dense, terrestrial-like bodies in tight orbits around a small dim red star, with at least 3 or 4 of them sitting in the part of the star's habitable zone where surface liquid water might be possible given the right atmosphere. Of those 3 or 4 habitable zone candidates, the planet that received the most attention from the start was TRAPPIST-1e. Part 3. The 7 and what their orbits do together. Before we go to TRAPPIST-1e specifically, it is worth a moment on the orbital structure of the system as a whole, because the structure tells you something about how the system formed and what it is doing now. The 7 TRAPPIST-1 planets are in orbital resonance. That means their orbital periods are not random numbers, they are integer ratios of each other, with each pair of adjacent planets completing some specific small number of orbits in the time the next planet completes another specific small number. Planet B completes 8 orbits for every 5 orbits of planet C. Planet C completes 5 orbits for every 3 of planet D. Planet D completes 3 orbits for every 2 of planet E. And so on, all the way out to planet H. The whole system is locked by gravitational interaction into a synchronized dance. There is a parallel in our own solar system that is worth pausing on. 3 of the 4 large moons of Jupiter, Io, Europa, and Ganymede are in a similar resonance, called the Laplace resonance, after the French mathematician Pierre-Simon Laplace, who first worked out the orbital dynamics in the late 1700s. Io completes 4 orbits for every 2 of Europa, and Europa completes 2 orbits for every 1 of Ganymede. The whole system of 3 moons is locked into a 4:2:1 ratio that has been stable for billions of years. Laplace, when he worked out the mathematics, did not have a planetary system around another star to compare to. He was simply describing what Galileo had observed in 1610 in the small refracting telescope from a balcony in Padua, when Galileo first saw that Jupiter had moons going around it. The Laplace resonance in our own system has been a textbook example of orbital dynamics for 220 years. The TRAPPIST-1 system, when its resonant structure was worked out in 2017, turned out to be a generalization of the Laplace resonance to 7 bodies instead of 3. The 7 planets, taken as a whole, form what astronomers sometimes call a Laplace chain. Each adjacent pair of planets is in a low-order resonance with the next. The whole system is locked by gravitational interaction into a synchronized set of integer period ratios. The mathematics, when you work it out, is more complicated than Laplace's 3-body case, but the underlying physics is the same. The system, by being resonant, is stable in a way that a non-resonant system with the same masses and orbital distances would not be. This kind of resonance is not unique to TRAPPIST-1, but it is rare in the catalogue of known exoplanet systems. Most systems we have studied have orbits that are roughly random in their period ratios. Resonant systems, when they occur, are interesting because they tell us something about the dynamical history of the system. Resonances are not random. They form when planets migrate in the presence of a protoplanetary disk and end up captured in the gravitational wells of integer period ratios with their neighbours. The TRAPPIST-1 planets in this picture formed somewhere in the disk around their host star, and as the disk dissipated, they migrated inward, and as they migrated, each one was captured in resonance with the next. The resonance, importantly, is what makes the system stable on long time scales. Without the resonance, the gravitational interactions between the 7 planets, all in tight, close-in orbits, would, on the time scale of millions of years, destabilize the system. Some planets would be ejected, others would collide. The system would not survive. With the resonance, the gravitational interactions are choreographed. Each planet's perturbation on its neighbours is in a specific phase relationship that, over many orbits, averages out and does not accumulate. The system, by being locked together, is stable. That stability matters for the question of habitability, because life, if it is going to arise on a planet, needs the planet to be in a stable orbit for billions of years. A planet whose orbit is changing dramatically on million-year timescales does not have the kind of climate stability that complex chemistry needs. The TRAPPIST-1 system, by being resonant and therefore stable, is at least, on this front, a good candidate for hosting life. The orbits will not change much on the timescales that matter for biology. There is one more consequence of the resonant structure that is worth noting, which is that the planets gravitationally talk to each other in ways that we can measure. The transit timing variations, which we use to infer the planetary masses, are very precise on this system, because the resonances make the perturbations large and predictable. Eric Aggle's 2021 paper, which used many years of accumulated transit timing data from Spitzer and ground-based observatories, was able to determine the masses of all 7 TRAPPIST-1 planets to a precision of better than 5%, that is, by the standards of exoplanet mass measurements, extraordinary. Most planets in most systems have mass estimates with uncertainties of 20 or 30% or more. The TRAPPIST-1 system, because of the resonant orbits and the long observational baseline, is one of the most precisely measured planetary systems anywhere outside our own. There is something genuinely remarkable about being able to measure the masses of 7 small planets, all at 40 light-years away, to a precision of better than 5%, by watching how they perturb each other's orbits over a decade of patient observations. Most planetary masses in our own solar system were not measured to that precision until well into the space age. The masses of Jupiter's moons, for example, were not known to 5% until the Voyager flybys in the late 1970s. The TRAPPIST-1 planets around a star 40 light-years away are now characterized to a precision that took us, in our own backyard, over 3 centuries to achieve. That is, by any reasonable accounting, a remarkable achievement of modern astronomy. The masses, when they came out, confirmed the earlier preliminary estimates. The 7 planets are all rocky. Some are slightly less dense than Earth, suggesting possible water content. Some are slightly more dense, suggesting iron-rich interiors. None of them is a gas giant. None is a Neptune. The system is, by any reasonable definition, a system of rocky worlds, like our own inner solar system, but compressed into a much tighter region of space, all orbiting a single, small, dim red star. Of those rocky worlds, 4 are in the habitable zone of TRAPPIST-1. Planets D, E, F, and G all receive amounts of starlight. That, given the right atmospheres, could allow surface liquid water. The 4 are, in some sense, 4 shots at habitability in a single system. The chances that at least one of them has the right combination of atmosphere, surface composition, and dynamic history to be actually habitable is, by this argument, 4 times as good as it would be for any single planet. The TRAPPIST-1 system is, in this respect, a target-rich environment. Let me sit with that for a moment. 4 of the 7 planets in the TRAPPIST-1 system are, by orbital geometry, in the part of the star's neighbourhood where surface liquid water might be possible. 4. Out of all the systems we have characterized carefully enough to assess, almost none have more than 1 habitable zone planet. Most have 0. TRAPPIST-1, with its 4, is, by this metric alone, an exceptional system. The probability that at least one of the 4 has the right combination of factors to actually be habitable is, by simple statistical argument, much higher than for any single planet around any other star. Of those four, TRAPPIST-1e is the one that, on every metric we currently have, is the closest to Earth. Part 4. Why TRAPPIST-1e specifically? To be clear, before we go further, the reason TRAPPIST-1e gets singled out among the four habitable zone candidates is not because it is, by itself, an obvious analogue to Earth. It is because, when you compare its measured parameters to Earth's, the agreement is, across the board, remarkably good. Better, by these specific metrics, than for any other exoplanet we have ever found. The radius of TRAPPIST-1e on the most recent measurements is about 91% of Earth's radius. That is closer to Earth than any other known habitable zone exoplanet. The mass of TRAPPIST-1e is about 69% of Earth's mass, slightly less than Earth, but in the same ballpark. The bulk density, when you compute it from the radius and the mass, comes out to about 93% of Earth's density. That density agreement, more than anything else, is what makes the case for TRAPPIST-1e being genuinely Earth-like in its bulk composition. Density tells you about the proportions of light and heavy materials in a planet's interior. A density similar to Earth's implies a similar balance of silicate mantle and iron core. A higher density would imply more iron. A lower density would imply more water or other lighter materials. TRAPPIST-1e, by being almost exactly Earth's density, is in its bulk composition very probably almost exactly Earth-like in the proportions of its rock and iron. So the planet is, in its overall composition, very similar to Earth, possibly slightly less iron-rich, possibly slightly more water-rich, but within the same broad family of rocky worlds. The orbital period of TRAPPIST-1e is 6.1 Earth days. That is, of course, much shorter than Earth's year, but the orbital period is not what determines whether a planet is habitable. What matters is the amount of energy the planet receives from its star. The host star, TRAPPIST-1, is much dimmer than the Sun. Its luminosity is about 5/1000ths of the Sun's. So even though TRAPPIST-1e is much closer to its star than Earth is to ours, the much fainter star delivers, in the end, an amount of light that is comparable to what Earth gets. The exact number, when you do the calculation, is that TRAPPIST-1e receives about 66% of the stellar irradiance that Earth receives. So the planet is, by this metric, slightly cooler than Earth would be if Earth were placed at TRAPPIST-1e's orbital position. The equilibrium temperature, calculated assuming Earth-like reflectivity, comes out to about -23 degrees Celsius. That is below the freezing point of water by a substantial amount, but it is comfortably within the range of temperatures where, given a thick enough atmosphere with greenhouse gases, surface liquid water could exist. Earth itself, without its atmosphere, would have an equilibrium temperature of about -18 degrees Celsius, also below the freezing point. The atmosphere, in both cases, is what makes the difference. The question, for TRAPPIST-1e, is whether it has an atmosphere of the right kind to make the difference. That question is, at the time of this telling, genuinely open. We will come back to it. The third reason TRAPPIST-1e gets attention is climate modelling. In 2017, around the time of the Nature announcement, several groups began running climate simulations of the TRAPPIST-1 planets, treating them as hypothetical worlds with various assumed atmospheres and surface compositions. The most influential of these early studies was led by an atmospheric scientist named Eric Wolf at the University of Colorado, Boulder. Wolf's models, when run for TRAPPIST-1e specifically, suggested that, for a wide range of plausible atmospheric compositions, the planet could support stable surface liquid water. The range of conditions under which TRAPPIST-1e could be habitable was, in his calculations, broader than for any other planet in the system. Wolf's models were, importantly, three-dimensional general circulation models, the same kind of complex atmospheric simulations that climate scientists use to model Earth's own weather and long-term climate. Running such models on a tidally locked exoplanet around a red dwarf required adapting the code, calibrating it for the different stellar spectrum, and accounting for the unusual atmospheric circulation patterns that develop on a planet with permanent day and night sides. The work was, by the standards of climate modelling, computationally demanding, each simulation, depending on the complexity of the assumed atmospheric chemistry, took weeks of supercomputer time to run. Subsequent modelling by other groups has refined the picture. Some models give a more pessimistic view, with TRAPPIST-1e being only marginally habitable under specific atmospheric conditions. Others give a more optimistic view. None of them has, to date, ruled the planet out. By the standards of climate modelling for exoplanets, where most candidates have a narrower range of habitable conditions, TRAPPIST-1e is, again, the most flexible candidate. It has the broadest range of plausible atmospheres that would still result in a habitable surface. There is an additional factor that contributes to TRAPPIST-1e's status as the best candidate, which is the observability. Among potentially habitable exoplanets known today, TRAPPIST-1e is one of the most observable, simply because of its host star. Small dim red dwarfs like TRAPPIST-1 give large transit signals for Earth-sized planets. Bright, sun-like stars with similar planets would give signals that are much harder to detect against the background of the much brighter host. The fact that TRAPPIST-1e orbits a small dim star means that its atmosphere, when it has one, leaves a strong fingerprint in the star's transmission spectrum during transit. This is not a feature of the planet itself in any direct sense. It is a feature of the planet's environment. But for the purposes of detailed characterization, the environment matters as much as the planet does. That accumulation of facts, the Earth-like radius, the Earth-like mass, the Earth-like density, the Earth-like irradiance, the broad climatic flexibility, is what makes TRAPPIST-1e, by every conventional metric, our best chance at finding another Earth. Not because it is, on its own, an obvious Earth analogue, because when you list the planets we know about and rank them by similarity to Earth across all of these metrics, TRAPPIST-1e is on top of the list. Let me sit with that for a moment. There are, on the most current count, somewhere between 5,000 and 6,000 confirmed exoplanets. The one that is most like Earth on every available metric is a small rocky world orbiting a small dim red dwarf 40 light-years away in Aquarius that no human eye has ever directly seen, around a star whose name is a number rather than a word, in a system that nobody knew existed before 2016. That is, in some sense, the deeper finding of the TRAPPIST-1 story, not the seven-planet system itself, not the orbital resonances, not the Earth-like sizes. The fact that, after 30 years of searching, our best candidate for another Earth is this small, dim world, with its red sky and its permanent twilight, around a star nobody can see. It tells you something about how rare Earth genuinely is. Part 5. Here is where the picture gets harder. Here is where the story of TRAPPIST-1e shifts, from the celebration of finding the best candidate to the harder question of whether the best candidate is actually any good. Because while TRAPPIST-1e looks, on paper, very much like Earth, the environment it sits in is, in important ways, very unlike Earth's. The host star is a small red dwarf, Red dwarf stars, even the relatively quiet ones like TRAPPIST-1e, are not like the Sun. They have different atmospheres, they have different spectral outputs, they have, throughout their long lifetimes, much more violent flaring activity than Sun-like stars. The combination of those differences means that the conditions on TRAPPIST-1e, even if the planet has an atmosphere of roughly the right composition for surface liquid water, may be very different from Earth's conditions in ways that could make life difficult or impossible. The first issue is the spectral output of the star. The Sun emits most of its energy in the visible part of the spectrum, with a peak in the green-yellow range that, not coincidentally, corresponds to the wavelengths that chlorophyll on Earth absorbs most efficiently. Red dwarfs, by contrast, emit most of their energy in the red and infrared parts of the spectrum. The visible light output of TRAPPIST-1e, if you could stand on the surface of TRAPPIST-1e and look up, would be much dimmer than the Sun looks from Earth, despite the planet being closer to its star. The infrared output, though, would be very strong. Most of the energy heating the planet's surface would be in infrared, not visible light. There is a small biological context worth pausing on because it tells you something about how unusual Earth's photosynthesis actually is. Chlorophyll, the molecule that makes plants green and that runs the dominant photosynthesis on Earth, absorbs light most strongly in the blue-violet part of the spectrum, around 430 nanometers, and in the red part, around 660 nanometers. The green wavelengths in between are where chlorophyll absorbs least efficiently, which is why plants reflect green light and look green. The molecule, in some real sense, is tuned to the spectrum of our Sun. The peak emission wavelength of the Sun, in the visible, sits in the green-yellow range, which is exactly where chlorophyll is least efficient. There is a quirk of evolutionary history here that is not fully understood. Chlorophyll could have evolved to absorb green light where the Sun's output is highest. It did not. Some atmospheric scientists have speculated that the original photosynthetic bacteria, billions of years ago, evolved in environments where green light was already being absorbed by other organisms, and the available niche was for an organism that could use the parts of the spectrum the others were not. By the time the green-absorbing organisms went extinct, the early evolved chlorophyll was locked in. For any photosynthetic life that might exist on TRAPPIST-1e, this is a different challenge from what life on Earth has solved. Photosynthesis on Earth uses chlorophyll-based pigments tuned to visible light. On a planet illuminated mostly by infrared, those pigments would not work. Life would have to evolve different pigments sensitive to longer wavelengths. Such pigments are possible. In principle, some of Earth's photosynthetic bacteria in deep ocean environments use bacteriochlorophyll, which is sensitive to near-infrared wavelengths, but the dominant photosynthesis on Earth, the one that produced the oxygen-rich atmosphere we breathe, uses visible light pigments. On TRAPPIST-1e, the equivalent biology would have to be different from the start. The second issue is tidal locking. TRAPPIST-1e, because it orbits its star so closely, is almost certainly tidally locked. One side of the planet permanently faces the star, the other side permanently faces away. The day side has perpetual reddish twilight. The night side has perpetual darkness. There are no seasons. There is no diurnal cycle. The same face of the planet has been pointed at the star in steady state for billions of years. There is a small but interesting consequence of tidal locking that climate models have to take into account, which is the wind patterns that develop on a tidally locked world. Earth, with its rapid rotation, has weather patterns dominated by Coriolis forces that drive the familiar mid-latitude jet streams and trade winds. A tidally locked planet, by contrast, has a fundamentally different atmospheric circulation, dominated by the temperature gradient between the day side and the night side. The wind, on a tidally locked planet, blows continuously from the substellar point toward the antistellar point, returning at higher altitudes to complete the global circulation. The jet streams in this picture are not east-west bands. They are radial flows from one specific spot on the planet to its antipode. This kind of circulation pattern has consequences for surface conditions. The substellar point, where the star is permanently overhead, becomes the warmest place on the planet. But the wind patterns also dominate the weather. Clouds, if they form, accumulate near the terminator, where the temperature gradient is steepest. Rain, if it falls preferentially in certain narrow bands. The whole climate on a tidally locked world is structured around the day-night divide in a way that has no equivalent in Earth's experience. Tidal locking on its own is not necessarily fatal for habitability. Climate models suggest that, with a thick enough atmosphere, heat from the day side can be redistributed to the night side by atmospheric circulation, keeping the night side from freezing over completely. But the redistribution depends sensitively on the atmospheric thickness and composition. Thinner atmospheres do worse. Atmospheres without enough greenhouse gases do worse. The window of conditions under which tidal locking is compatible with global habitability is narrower than for a non-tidally locked planet. The third issue, and the one that has come into sharper focus over the past decade, is stellar flaring. There is a small but important context about stellar flaring that is worth introducing here, because the term means something different in M-dwarf astronomy than it does in solar physics. On our own Sun, a typical large flare releases about 10 to the 25th joules of energy. The Carrington event of 1859, which was the largest solar flare in recorded human history, was perhaps a few times this. It produced auroras visible at the equator and disrupted telegraph systems around the world. By the standards of solar physics, that was an extreme event, the kind we expect once every 100 years or so. On a small red dwarf like TRAPPIST-1e, flares of similar absolute energy occur much more frequently, perhaps several times a year. And because the star itself is so much dimmer in its quiescent state, the flares are, in relative terms, enormous. A flare that is the same absolute energy as a Carrington event on a star that is 5,000 times fainter than the Sun is, in proportion to the star's normal output, many thousands of times more significant. The high-energy radiation, especially in the ultraviolet and X-ray bands, can briefly exceed the star's normal output by orders of magnitude. The planets, which receive most of their illumination from the same star, experience these flares as enormous transient spikes in radiation. Whether those spikes do significant damage to a planet's atmosphere or to any life that might exist on its surface depends sensitively on the planet's atmospheric thickness, magnetic field strength, and orbital distance from the star. A thick atmosphere can absorb most of the high-energy radiation before it reaches the surface. A strong magnetic field can deflect charged particles. A more distant orbit means the energy density at the planet falls off with the square of distance. None of these protections is absolute, but in combination they can substantially reduce the cumulative damage from flares over geological time. The question, for any specific planet around any specific red dwarf, is whether the protections are sufficient. Part 6. The flaring question. Red dwarf stars, including TRAPPIST-1 itself, are known to produce stellar flares. Stellar flares are sudden brightenings of the star caused by magnetic reconnection events in the star's atmosphere that release enormous amounts of energy in the form of high-energy, ultraviolet, X-ray, and charged particle radiation. The Sun produces flares too, but the flares of an M-dwarf, even a relatively quiet one like TRAPPIST-1, are much more energetic relative to the star's normal output, and much more frequent. There is a useful comparison with our own Sun that helps put the TRAPPIST-1 flaring picture in context. Our own Sun, on the time scale of human civilization, has been quiet. The Carrington event of 1859 is the largest documented solar storm, and it produced effects that were noticeable but not catastrophic. The Sun has flares all the time, but the flares are a small fraction of its normal output, and the planets, including Earth, have absorbed the cumulative flaring over the 4.5 billion years since the Sun was born without any obvious damage to long-term habitability. The Sun, by red dwarf standards, is a very mild flarer. Most of the cosmic radiation environment that life on Earth has had to deal with has come from outside the solar system, not from the Sun itself. A red dwarf flarer is different. The flares are larger, in proportion to the star's normal output. They are more frequent. They produce more high-energy radiation in the ultraviolet and X-ray bands. The cumulative effect on a planet in the habitable zone of a red dwarf is much more substantial than the cumulative effect of solar flaring on Earth has been. Whether this makes red dwarf habitable zones genuinely uninhabitable or merely difficult is the central question. The atmospheric measurements we are now starting to make on the TRAPPIST-1 planets are the first direct test of which answer is correct. The first careful observations of TRAPPIST-1's flaring activity came in 2017, shortly after the 7-planet announcement, when several teams pointed time-domain instruments at the system to look for variability. The K2 mission, the second life of the Kepler Space Telescope, after its reaction wheels failed, observed TRAPPIST-1 for about 80 days in 2016. The data, when analysed, showed flaring events at a rate of about 1 significant flare per couple of days, with energies that, while smaller than the Sun's biggest flares, were larger relative to the star's quiescent output. What this means for the habitability of TRAPPIST-1e is genuinely uncertain. A single flare on its own would not strip an atmosphere or sterilize a planet. But the cumulative effect of repeated flares over billions of years could be substantial. The high-energy ultraviolet radiation from a flare can drive photochemistry in a planet's upper atmosphere, breaking apart molecules and creating reactive species. The X-ray radiation can heat the upper atmosphere directly, causing it to expand and lose mass to space. The charged particle radiation, if the planet has a weak or absent magnetic field, can interact directly with the surface and the lower atmosphere, doing chemistry that, on Earth, is largely prevented by our magnetic field. The combined effect of these processes, integrated over billions of years, is the question that determines whether TRAPPIST-1e currently has any atmosphere at all. If the planet started with an Earth-like atmospheric inventory, and the processes drove atmospheric loss at a rate of a few % per million years, then over 4 billion years, a substantial fraction of the original atmosphere could be gone. Perhaps most of it, perhaps almost all of it. The bare rocky surface exposed to the full ultraviolet flux of the host star would be a sterile environment. Any life that had managed to begin in earlier eras would, by now, have nowhere to live. This is the picture that, in 2023, became more concrete with new observations. Part 7. The first JWST observations. There is a small piece of context worth adding about JWST's role in this story. The telescope was launched in December of 2021, after almost 3 decades of design, construction, and delays. By the time it reached its operating position at Lagrange Point 2 and finished its commissioning phase in mid-2022, it had become, by a wide margin, the most capable infrared instrument in human history. Its primary mirror, 6.5 meters across, gives it light collecting area more than 6 times that of Hubble. Its detectors, in the infrared range where most exoplanet atmospheric features sit, are far more sensitive than anything previously available. The TRAPPIST-1 system, as a high-priority target, was on JWST's observing list from the very first cycle of allocated time. In 2023, the James Webb Space Telescope began its first dedicated observations of the TRAPPIST-1 system. The first target partly because it was the easiest to observe and partly because it was a useful baseline was TRAPPIST-1e, the innermost and hottest planet. A team led by an astronomer named Thomas Green at NASA's Ames Research Center used JWST's MIRI instrument to measure the planet's thermal emission and to look for atmospheric signatures. The result, when it came in, was significant. TRAPPIST-1b on the JWST measurements has no detectable atmosphere. The planet's thermal emission is consistent with a bare, rocky body with no insulating atmospheric layer. The day side is hotter than it would be with an atmosphere because there is no atmospheric circulation to carry heat to the night side. The night side is correspondingly very cold. Green and his team published the result in Nature in March of 2023. The paper was, by exoplanet science standards, a major event. The first definitive characterization of the thermal emission of any TRAPPIST-1 planet, with confidence sufficient to rule out a substantial atmosphere, was a real result. The press coverage was, however, mixed. Some outlets reported the result as bad news for the TRAPPIST-1 system as a whole, suggesting that all 7 planets might be airless. Others reported it more cautiously, noting that the result on the innermost, most exposed planet did not necessarily say anything definitive about the more distant ones. The mixed coverage was, in some sense, an accurate reflection of the genuinely uncertain implications. What TRAPPIST-1b's lack of atmosphere means for TRAPPIST-1e is a question the data alone does not answer. That result was, on its own, not entirely surprising. TRAPPIST-1b is the closest planet to its star, receives the most flux, and is the most exposed to atmospheric stripping. The fact that it has been stripped down to a bare rock is consistent with the picture that close-in planets around active red dwarfs lose their atmospheres on geological timescales. But the result was also concerning, because it raised the question of whether the same fate had befallen the more distant planets in the system. If TRAPPIST-1b has no atmosphere, what about TRAPPIST-1c, TRAPPIST-1d, TRAPPIST-1e? The atmospheric stripping rate falls off with distance from the star, but the more distant planets are also subject to the cumulative effect of billions of years of stellar flaring. Whether the rate of stripping has been slow enough on TRAPPIST-1e to allow the planet to retain a significant atmosphere is genuinely uncertain. There is a small piece of context worth adding about JWST observing time, because it tells you something about the practical constraints of this kind of work. JWST is by far the most oversubscribed telescope ever built. For every hour of observing time available, dozens of teams compete with proposals. The proposals are reviewed by panels of scientists, ranked, and the best ones are awarded time. The TRAPPIST-1 system, because of its scientific importance, has consistently received high-priority observing time in every cycle so far. But the time is limited. Each transit of TRAPPIST-1e takes about an hour to observe. Building up enough transits to detect a thin atmosphere requires dozens of hours of integrated time. Each cycle of JWST observations, therefore, only accumulates a few transits worth of data on TRAPPIST-1e. The full atmospheric characterization will require many cycles over many years to accumulate. JWST observations of TRAPPIST-1e specifically have begun, but as of the time of this telling, the data is still being processed and analyzed. The atmospheric question for the planet that matters most has not yet been definitively answered. Early results suggest that, at a minimum, TRAPPIST-1e does not have a hydrogen-helium-dominated puffy atmosphere. The transmission spectrum in the data analyzed so far would show characteristic features of such an atmosphere if it existed, and those features are not present. So the planet is not a mini Neptune. Beyond that, the data is consistent with several possibilities: a thick CO2 atmosphere, a thin atmosphere, or no atmosphere at all. The next several years of JWST observations should narrow the picture. I am not saying that TRAPPIST-1e has no atmosphere. I am not saying that it has one. I am not saying that it is or is not habitable. What I am saying is something quieter than any of those. What I am saying is that, on the best evidence we currently have, the planet has not been ruled in or ruled out. The future of the question depends on observations that have not yet been completed. By the late 2020s, with sufficient JWST observing time accumulated, we should know much more than we know tonight. Part 8. What life on TRAPPIST-1e might look like. For a few minutes, let me describe what TRAPPIST-1e probably actually is in physical terms, with the level of detail that current models support. This is the closest I can get, in words, to taking you there. You arrive in the upper atmosphere of TRAPPIST-1e, somewhere on the day side in a hypothetical scenario where the atmosphere is thick enough for the planet to be habitable. The atmosphere around you is most plausibly nitrogen-dominated, with a substantial fraction of carbon dioxide for greenhouse warmth and possibly water vapor at lower altitudes. The pressure at your altitude, depending on which atmospheric model you favor, is somewhere between half an Earth atmosphere and a few times Earth's atmosphere. The temperature in this scenario is moderate, perhaps just above freezing, perhaps slightly warmer depending on the local position and the time-averaged irradiance. Above you, the star takes up a noticeable angular extent in the sky. The host star, TRAPPIST-1, is small in absolute terms, but the planet is so close to it that the angular diameter from the planet's surface is about 3 times what the Sun looks like from Earth. The color is a deep dim red, like the color of a hot ember in a fireplace, or the dying glow of a sunset that has already set most of the way below the horizon. The light reaching the surface is, in human visual terms, dim. Perhaps a tenth of the brightness of overcast noon on Earth. The whole world is bathed in a kind of permanent reddish twilight that no human eye has ever directly seen. Below you, if the atmospheric model is right, the surface might be habitable. There might be oceans. There might be land. The planet's rocky composition, similar to Earth's, suggests that surface water and atmosphere can interact in the same kinds of ways they do on Earth, with weathering of silicate rocks providing the carbon dioxide drawdown that, on Earth, is a key part of the carbon cycle. The chemistry of a habitable TRAPPIST-1e in this picture would not be utterly alien, it would be Earth-like in many of its broad outlines, but with the details adjusted for the different stellar input. The day side, where the star is permanently overhead, would be the warmest part of the planet. The night side, where the star never appears, would be the coldest. The atmospheric circulation, driven by the temperature difference between the two, would carry heat from the day side to the night side, keeping the night side from freezing over. The pattern, in 3 dimensions, would be a continuous global wind from the substellar point on the day side to the anti-stellar point on the night side, with the return flow happening at higher altitudes. The substellar point, where the star is permanently overhead, would have its own particular character. The star would be at zenith, never moving, never rising, never setting. The temperature at the substellar point would be the warmest on the planet. Possibly warm enough for liquid water on the surface, perhaps even small lakes or oceans. The wind, if you stood there, would be drifting from all directions, since the substellar point is the center of the global atmospheric circulation. Above you, the dim red star would hang motionless. Behind you, in any direction you turned, the planet would extend out toward the terminator, where the perpetual twilight would slowly fade into the night side. If you walked in some hypothetical way from the substellar point toward the terminator, the temperature would gradually fall, the wind would gradually pick up, and the color of the sky would gradually shift. By the time you reached the terminator itself, you would be in a permanent twilight zone where the star is just at the horizon, perpetually setting, but never quite gone. If you crossed the terminator, you would enter the night side, where the star is permanently absent. The temperature is much colder, and the only illumination would be the dim glow of the day side terminator on the horizon behind you. The whole walk, from substellar to antistellar, would be a journey through a fixed atmospheric and thermal landscape, with the conditions of each location determined by the star's permanent position rather than by any time of day cycle. The light environment would be unlike Earth's. Photosynthetic life, if it existed, would have to use pigments that absorb at red and infrared wavelengths rather than the green-yellow ones that chlorophyll uses. The color of any plant cover on the surface might be black or purple or some color we have not seen before. The skies overhead, depending on atmospheric chemistry, might be reddish or pinkish or some other shade of long wavelength tint. Standing on the surface, looking up, you would not see anything that resembled an Earth sky. You would see something genuinely new. There is one more sensory detail worth painting, which is what the night sky on a hypothetical habitable TRAPPIST-1e would look like. Because the planet is in a tight, close-in orbit, the other planets in the system are, to an observer on the surface, much more visible than the planets of our own system are to an observer on Earth. Saturn, from Earth, looks like a faint star to the naked eye, no different from any other star except for its specific position. Venus and Jupiter, at their brightest, are slightly more dramatic, but still essentially point sources. On a hypothetical TRAPPIST-1e, the other planets in the system would appear at their closest approaches as visible disks, bright, distinct, sometimes showing surface features that would be detectable to the naked eye. The neighbouring planets, TRAPPIST-1d and TRAPPIST-1f, would be the most visible. They would orbit at distances close enough that, when they passed near TRAPPIST-1e, they would appear several times the size of our moon in the sky, bright, round, coloured according to their actual surface, compositions and atmospheric tints. The night sky of TRAPPIST-1e in this picture would not be a sky of point-like stars the way Earth's night sky is. It would be a sky of visible neighbours, other worlds, close enough to be seen as worlds. The whole system, if you could stand on the surface of TRAPPIST-1e and watch the sky, would be a different kind of cosmic neighbourhood than the one we are used to. This is, of course, all speculative. We do not know whether TRAPPIST-1e has the atmosphere this scenario assumes. We do not know whether life has arisen there. We do not know what the surface looks like. The picture I am painting is the picture of a habitable TRAPPIST-1e in the best-case scenario, given everything we currently know about the planet. The actual TRAPPIST-1e, when we eventually characterize it in more detail, might match this picture. It might not. The question is open. Let me sit with that for a moment. The most Earth-like planet we have ever found when we paint a picture of what it might be like is genuinely strange. Permanent twilight, red light, no seasons, no diurnal cycle, photosynthesis, if there is any, on different pigments. The best chance at another Earth is, when you actually look at it, not very Earth-like at all. Part 9. The system as a laboratory. One of the most useful features of the TRAPPIST-1 system, beyond the question of TRAPPIST-1e itself, is that the 7 planets together provide a kind of natural laboratory for studying how Earth-sized worlds evolve under the conditions of red dwarf irradiation. The planets, all formed from the same protoplanetary disk around the same star, sit at different distances and therefore have received different cumulative doses of stellar radiation over their lifetimes. By comparing their current properties, we can, in principle, separate the effects of stellar irradiation from the effects of other physical processes. The innermost planets, B and C, have been the most exposed. They have received the most ultraviolet radiation, the most X-ray radiation, and the most charged particle bombardment. They have also been subject to the strongest tidal forces and the strongest atmospheric stripping. The current state of these planets, as the JWST observations of TRAPPIST-1b have shown, includes at least one body that has been stripped to a bare rock with no atmosphere. The middle planets, D, E, and F, have been less exposed. They sit at intermediate distances where the irradiation is lower but still substantial. The atmospheric loss rates on these planets depend sensitively on the assumed magnetic field strength of each planet, on the composition of the original atmosphere, and on the cumulative flaring history of the host star. Different models give different answers. The observational data, by 2025, was just beginning to constrain these parameters. The middle planets will be where the question of habitability is actually resolved as more JWST observing time is accumulated. The outer planets, G and H, have been the least exposed. They are also the coldest, with surface equilibrium temperatures well below freezing for any plausible atmosphere. Habitable surface conditions are possible for these planets only with very thick greenhouse atmospheres, and even then, the habitable range is narrow. They are interesting objects in their own right, but they are not the primary candidates for Earth-like surface conditions in the system. The comparative study of all 7 planets, then, is one of the major scientific values of the TRAPPIST-1 system. By measuring the atmospheres and surface properties of each one and comparing the results, we can build up a picture of how Earth-sized planets respond to the conditions of red dwarf systems in a way that no single planet around any other star would let us do. The 7 TRAPPIST-1 planets are, in this respect, more valuable than 7 random rocky worlds at random distances from random stars. They are a controlled experiment. There is a methodological point worth making here, which is that the comparative study of 7 similar planets around a single star is fundamentally different from the comparative study of 7 planets around 7 different stars. Around different stars, the planets formed in different conditions with different initial volatile inventories, around stars with different histories of activity. Almost any comparison you do is confounded by the differences in formation environment. Around a single star, the formation environment is, to a first approximation, the same for all 7 planets. The differences in current properties, then, are attributable to the differences in orbital distance and the consequent differences in stellar irradiation and dynamical history. The TRAPPIST-1 system, in this respect, is a controlled experiment that no other system in the catalogue currently provides. The scientific value of having 7 planets around one star in resonance, all reasonably well characterized, is hard to overstate. The next decade of JWST observations will fill in the picture. Each new transmission spectrum, each new emission spectrum, each new phase curve will add another data point to the comparative study. By the late 2030s, the picture should be substantially complete. The atmospheres of all 7 TRAPPIST-1 planets should be characterized, at least in their broad outlines. The pattern of how the atmospheres vary with distance from the star should be visible. The implications for habitability of red dwarf planets in general should be understood in a way that is not currently possible. There is a parallel here with our own solar system that is genuinely useful. Our own inner solar system contains 4 rocky planets, Mercury, Venus, Earth, and Mars, all formed from the same protoplanetary disk, all at different distances from the Sun. The comparative study of these 4 worlds over the past century has taught us almost everything we know about how rocky planets evolve under different stellar irradiation conditions. Mercury, with no atmosphere, tells us what happens when a small planet is too close to its star. Venus, with its runaway greenhouse, tells us what happens when an atmosphere goes wrong. Earth, in its sweet spot, tells us what habitability looks like. Mars, with its thin atmosphere and its frozen surface, tells us what happens when a planet starts in the habitable zone, but loses its atmosphere over time. The TRAPPIST-1 system in 7 planets gives us a similar comparative laboratory, but for a different kind of star. The lessons we will eventually extract from the comparative study of TRAPPIST-1's 7 worlds will be, in their broad outlines, the same kind of lessons we extracted from the comparative study of our own 4. They will tell us what happens to rocky planets at different distances from a small red dwarf and how the answers differ from the answers around a sun-like star. Together with our own solar system, the TRAPPIST-1 data will give us 2 well-characterized inner systems to compare. The comparison will be one of the more important products of modern exoplanet science. That kind of comparative study on a single system is one of the more valuable scientific outcomes of the TRAPPIST-1 discovery. It is, in some sense, more valuable than finding any one habitable planet would be, because what we are learning is not just about TRAPPIST-1e specifically. We are learning about a whole class of worlds. Part 10. The honest accounting of best chance. Here is where I want to be honest about what our best chance at another Earth actually means, given everything we have just walked through. I am not saying that TRAPPIST-1e is Earth-like. I am not saying it is habitable. I am not saying it has life on it. I am not saying that when we finally characterize its atmosphere in detail, we will find conditions that we would consider familiar. What I am saying is something more limited. By the metrics we currently have for ranking exoplanets by their similarity to Earth, this planet ranks at the top of the list, not because it is on its own a strong analogue, because the list is short, and the candidates are few, and the alternatives are worse. The honest assessment by 2025 is that we do not know whether TRAPPIST-1e is habitable. We do not know whether it has an atmosphere. We do not know whether it has surface liquid water. We do not know, even if it has all of these things, whether life has arisen there or could arise. The question of habitability on this planet is one that JWST and the next generation of telescopes are starting to address but have not yet answered. Whatever we say tonight is provisional, and the picture in 2035 will be better than the picture tonight. What we can say with some confidence is that the situation is, by every available metric, the most favourable it could be. The planet is the right size, it is the right mass, it is at the right orbital distance, it is in the right kind of stellar system to allow detailed atmospheric characterization. It is close enough to Earth at 40 light-years to be observed with current and near-future instruments. The technology to answer the question of its habitability either exists or is being built. By the timescales of human science, the answer should arrive within a generation. That accumulation of favourability, the right size, the right mass, the right orbit, the right star type, the right distance, the right instruments, is what makes TRAPPIST-1e our best chance. Not because the chance is high, because by every variable we control or can affect, the conditions are right for getting an answer. Whether the answer will be yes or no is, of course, what we do not yet know. Part 11. Why this matters even if the answer is no. Here is the thought that I find most compelling when I sit with the TRAPPIST-1e story. The question of whether this specific planet is habitable is, in some ways, less important than the question of what we learn by trying to find out. Consider the alternative outcomes. If TRAPPIST-1e turns out to be habitable with a thick atmosphere and surface liquid water and chemistry that supports life, that will be a profound discovery. It will tell us that Earth-like worlds, at least in red dwarf systems, are not vanishingly rare. The galaxy, if TRAPPIST-1e is habitable, will turn out to be a place where habitable planets are reasonably common. If TRAPPIST-1e turns out to not be habitable with a thin atmosphere or no atmosphere, that will also be a meaningful discovery. It will tell us that the conditions of red dwarf systems, even for planets in the right orbital range and with the right physical properties, are hostile to life. The vast majority of stars in our galaxy are red dwarfs. If habitability around them is generally hostile, the galaxy is, by a wide margin, less hospitable than we might have hoped. There is a third possibility that is worth taking seriously, which is that TRAPPIST-1e turns out to have a thin or moderate atmosphere that is not obviously habitable, but not obviously sterile either. The atmosphere might support some surface chemistry, but not surface liquid water at most locations. Or it might support liquid water in some narrow band near the terminator, but not over most of the day or night side. Or it might support active volcanism replenishing the atmosphere, but not enough to maintain a fully habitable surface climate. The intermediate cases on close examination may be the most common outcome for many candidate worlds. The clean dichotomy between habitable and not habitable may, in practice, give way to a spectrum of intermediate conditions that the next decade of observations will reveal. If TRAPPIST-1e turns out to be one of those intermediate cases, that result is also informative. It tells us that the path from physically possible to be habitable to actually habitable is harder than the simple models suggest. It tells us that, even with the right size, mass, and orbital distance, the additional conditions required for a fully habitable surface are demanding. The galaxy, in this picture, would be full of planets that almost qualify but do not quite. The few that do qualify would be, by the standards of this picture, especially valuable, both as scientific targets and as places to imagine in any kind of future-looking conversation about life beyond Earth. Either result, in other words, changes our picture of how common Earth-like worlds are. The middle outcomes, ambiguous results that leave the question open, are also informative, because they will narrow the parameter space within which habitability questions are answered. That is, in some sense, why this work is worth doing regardless of the eventual answer. We are not, in the strict sense, looking for Earth twins. We are looking for the boundaries of where habitability is and is not possible. TRAPPIST-1e is a particularly informative test case because it has so many of the favourable features. If the planet is habitable, the boundary is wide. If it is not, the boundary is narrow. The information value of the answer is, by the standards of modern astronomy, very high. That is not the kind of justification that makes for a snappy headline. The best chance at another Earth is, in part, marketing. The slow, careful work of building up our picture of where life can and cannot exist by examining every available test case in detail is the actual science. The marketing draws attention. The science, beneath the attention, does the work. Both are needed. Neither, on its own, would be enough. Part 12. The next decade of observations. I'm not saying that TRAPPIST-1e is sterile. I'm not saying it cannot support life. I'm not saying that the next round of observations will rule it out as a habitable candidate. What I'm saying is something quieter than any of those. What I'm saying is that the question as it stood in 2017 looked easier than it has turned out to be. The best chance at another Earth on close examination is a chance with significant complications attached, and the complications are real. Whether those complications add up to a non-habitable verdict, a habitable verdict, or some intermediate result is something the next decade of careful observations will answer. We do not yet know. We are, in some sense, still in the early chapters of the TRAPPIST-1 story. The next decade of JWST observations, plus the planned observations from upcoming missions, will substantially improve our picture of TRAPPIST-1e. The James Webb Space Telescope will continue to observe the system, with progressively longer integration times accumulating on the planets that are most likely to host atmospheres. The European Space Agency's Ariel mission, scheduled to launch in 2029, will provide a complementary survey of exoplanet atmospheres at slightly lower precision, but on a much larger sample of planets, including the TRAPPIST-1 planets. The ground-based, extremely large telescope, with its 39-metre primary mirror, will see first light in the late 2020s. From a mountaintop in Chile, the ELT will be able to do high-resolution spectroscopy of the TRAPPIST-1 planets in ways that no current ground-based instrument can. By 2035 or so, the combined picture from JWST, Ariel and the ELT should be substantially complete. There is a piece of context worth adding about Ariel specifically, because the mission has been designed in some respects with the TRAPPIST-1 system in mind. Ariel stands for the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and its primary scientific goal is to characterize the atmospheres of about 1,000 exoplanets at moderate spectral resolution. The mission will not match JWST in raw sensitivity for any single target, but it will provide consistent, calibrated atmospheric measurements across a much larger sample, allowing comparative studies of populations of planets that JWST, with its limited observing time, cannot match. The TRAPPIST-1 planets are on the aerial target list, and the mission's data, when combined with JWST's, will provide independent confirmation of any features detected and a fuller picture of the atmospheric structure of the system. Beyond these, the next-generation flagship missions, including the Habitable Worlds Observatory planned for the 2040s, will take the work to a different level. Direct imaging of exoplanet atmospheres separating the planet's light from its stars will become possible for nearby small worlds in the HWO era. The TRAPPIST-1 system will by then be one of the standard reference targets, much as 55 Cancri E and HD 189733b have been standard reference targets for the previous generation. The catalogue of well-characterized, potentially habitable worlds by the 2040s should number in the dozens. There is a deeper way of looking at the question of TRAPPIST-1e's habitability that is worth pausing on. The question is not, in the strict scientific sense, does this planet have life on it? The question is, what does this planet's atmospheric chemistry look like? And what does that chemistry tell us about whether life could exist on its surface? The first question is, with current and near-future instruments, almost impossible to answer definitively. The second question is, with current and near-future instruments, very much answerable. The two questions are related, but not the same. The work that JWST and Ariel and the ELT are doing in characterizing TRAPPIST-1e's atmosphere is the work of answering the second question. Whether the answer to the second question implies an answer to the first is a separate, more philosophical, more difficult question that the data alone may never fully resolve. That distinction matters, because it tells you something about what the science of exoplanet habitability can and cannot tell us in any specific generation. We can measure atmospheres, we can measure surface temperatures, we can measure compositional spectra. We cannot, in any direct sense, measure life. The question of life, when it is finally answered, will be answered by a combination of atmospheric chemistry that is consistent with biological activity, plus the absence of plausible, non-biological explanations for that chemistry, plus repeated independent confirmations across multiple instruments and multiple techniques. The answer, when it comes, will be probabilistic, not certain. We will, in some sense, infer life rather than directly observe it. Whether TRAPPIST-1e specifically turns out to be habitable, or whether it turns out to be one of the many candidates that fall just short, the work of the next 2 decades should, almost certainly, produce a definitive answer. The instruments are being built, the observing time is being allocated, the teams are being trained. By the time today's children are entering middle age, the question of what TRAPPIST-1e is actually like should be largely closed. That time scale is worth pausing on. The children, who are being born this year in 2026, will be in their late 30s or early 40s when the comprehensive characterization of TRAPPIST-1e is, on the most current estimates, complete. They will read the answer in their working lives as a settled fact of the universe. They will know whether one of the 7 planets in this small, obscure system has surface liquid water, or has an atmosphere, or is sterile, or supports the chemistry of life. They will know it by the time they are in middle age in the same way we know the basic facts of our own solar system. As background knowledge of how the universe is arranged, we will not know it, most of us, in our own lifetimes. The work is too slow, the instruments too rare, the observations too oversubscribed. We will have, by the end of this decade, a partial picture. We will have, by the end of the next, a much better picture. We will pass the torch, then, to the generation that will see the answer. That time scale, again, is one of the more remarkable features of this kind of work. Most fields in modern science have answers on the time scale of years or decades. Exoplanet atmospheric science, particularly for small habitable zone worlds, has answers on the timescale of a generation. The patience required is genuine. The reward, when it comes, is rare and often quiet. The work, beneath both, continues. Part 13. The view from 40 light years. 40 light years is, in cosmic terms, very close. The light from TRAPPIST-1 reaching Earth tonight left that star around the year 1985. Anybody alive in 1985 was alive when the photons that confirmed the chemistry of TRAPPIST-1e decades later started their journey toward us. That short time scale matters because it means the system is, in some practical sense, accessible. Communication, in the very long-term sense, would be theoretically possible on a human timescale. A radio message sent from Earth to TRAPPIST-1 would take 40 years to arrive. A reply, if there were anybody on TRAPPIST-1e to send one, would take another 40 years to come back. The round trip is 80 years, which is shorter than a human life. A message could, in principle, be sent and answered within a single generation. There is, of course, almost certainly nobody on TRAPPIST-1e to send a reply. The communication thought experiment is purely theoretical, but the proximity matters because it tells you something about what is in reach. There is a sense in which the proximity of TRAPPIST-1 turns the question of habitability into a question about us, as well as a question about the planet. If TRAPPIST-1e is habitable, it is one of a small number of relatively nearby places where the conditions for life apparently exist. The implications for any future human consideration of expanding our presence beyond Earth are not zero. The implications for the philosophical question of whether we are alone are also not zero. The proximity makes both questions, in some sense, relevant to our own future, in a way that more distant candidates would not. The Breakthrough Starshot project, an initiative announced by Russian-Israeli billionaire Yuri Milner in 2016, has proposed sending tiny probes to nearby star systems using laser-driven solar sails. The technology, if it were developed to maturity, could in principle reach speeds of about 20% of the speed of light. At that speed, a probe to TRAPPIST-1 would take about 200 years to arrive, plus another 40 for the data to come back. That is a long time, but not an impossibly long time. The Brooklyn Bridge has been standing for about 140 years. It is, in human institutional terms, the kind of timescale that some institutions can plan for. The Starshot probes in their original design would carry small cameras and basic instrumentation. They would, on arrival at the target system, conduct a flyby observation that would last perhaps a few hours and would then transmit the data back to Earth via laser communication. The data return would, given the distance, be limited. There is something in the Starshot proposal that I find genuinely compelling, even if the technology never gets built. It is the explicit acknowledgement that some scientific questions are worth the multi-generational commitment that interstellar work would require. Most institutions do not plan in any serious way for projects that take centuries to complete. The Starshot proposal does. Whether the specific technical approach is correct, whether the funding ever comes together, whether the political and economic conditions allow such a project to actually launch, is all uncertain. But the idea that humans might be willing to start something now whose results would only be known by people not yet born is a quietly remarkable one. It is the kind of intergenerational thinking that has built in earlier eras the cathedrals and the universities and the long traditions that have outlasted any individual human life. The Starshot proposal, even in its current speculative form, is a continuation of that tradition. Bandwidth from 40 light-years away, even with a powerful laser, is small. The probes would send back images and basic atmospheric measurements, not the kind of detailed characterization that current space telescopes can already do remotely. Whether the cost of building, launching, and receiving data from such probes would be justified by the additional information they would return is a genuine, open question. The answer probably depends on what we have already learned from remote observations by the time the probes would arrive. Whether such a probe is ever actually built is, of course, a different question. The technology required is well beyond what has been demonstrated. The political and economic commitment required is enormous. The patience required on the part of whatever institutions would launch the probe and receive its data centuries later is unprecedented. By the standards of any human endeavour, the Starshot vision is ambitious to the point of probable infeasibility. But the proximity, regardless of whether we ever send a probe, matters for the science. The TRAPPIST-1 system is, by current measurements, at roughly the closest distance at which a system of 7 Earth-sized planets has been found. The proximity also makes the system observable by JWST, with reasonable integration times. A more distant system would require correspondingly longer observations to get the same signal-to-noise on its atmospheric features. TRAPPIST-1, by being at 40 light-years rather than 400, gives us atmospheric spectra of acceptable precision in a few transits worth of observation. A system at 400 light-years would require dozens or hundreds of transits to reach the same precision, which would be impractical given the limited observing time available on JWST and similar instruments. The proximity in this sense is not just a philosophical convenience, it is a practical necessity for the kind of detailed atmospheric work we want to do. There is, in fact, no other comparable system known anywhere in the local neighbourhood. The TRAPPIST-1 system in 2025 remains the only known system of 7 Earth-sized planets in resonant orbits around a single nearby star. Other systems with multiple potentially habitable planets exist, but none has the same combination of features that make TRAPPIST-1 such a uniquely valuable target. The closest comparable systems in terms of having multiple Earth-sized planets in habitable orbits are at distances of hundreds of light-years rather than tens. The atmospheres of those more distant systems will be much harder to characterize, and the data will inevitably be lower precision. The next closest comparable system, when it is found, will probably be at greater distance and therefore harder to study. TRAPPIST-1, in that sense, is genuinely fortunate. The system that is most observable at the highest precision with the current and next-generation instruments is also one of the most interesting. The accident of geometry has placed our best test case for red dwarf habitability within reasonable reach of our best instruments. That is the kind of small, lucky alignment that makes modern astronomy possible. The information has been arriving on Earth for as long as the Earth has existed. The instruments capable of reading it have only existed for a few decades. The systems that the instruments are best at characterizing are the ones that happen to be in the right configuration. TRAPPIST-1, by being at 40 light-years with 7 planets in resonant orbits around a small dim star, is in exactly the right configuration. It is, in some sense, a gift of the geometry. Part 14. Coming Home. We did not set out to find another Earth. We set out in the early 2010s to find planets at all. The TRAPPIST survey, with its small telescopes and its modest budget, was looking for any planets it could find around any small, dim red stars in the local neighbourhood. The 7-planet system, when it was discovered, was a surprise. The Earth-like sizes were a surprise. The orbital resonances were a surprise. The fact that one of the planets, on the metrics we use, would turn out to be the most Earth-like world ever found was a surprise on top of a surprise. That is the temperament of this kind of work. The discoveries do not come from a master plan. They come from a slow accumulation of careful observations by small teams with modest equipment, looking at systems that nobody had paid much attention to before. TRAPPIST-1 in 2015 was just one more obscure red dwarf in the catalogue. By 2017, it was the most famous exoplanet system in the world. By 2025, it is the central reference target for the question of whether Earth-like life is possible around the most common kind of star in the galaxy. There is a thought worth holding before we end about the time scale of the work we have just walked through. The TRAPPIST telescope started observing in 2010. The first 3 planets were announced in 2016. The full 7 were announced in 2017. The first JWST observations of the system began in 2022. The first definitive atmospheric results on TRAPPIST-1e came in 2023. The full atmospheric characterization of TRAPPIST-1e, when it is finally complete, will probably come somewhere in the early 2030s. From the start of observations to the answer, 25 years or more. That is not a slow time scale by the standards of cosmic scale science. It is, in fact, fast. 3 decades from the discovery of the first exoplanets in the early 1990s to the detailed atmospheric characterization of nearby Earth-sized worlds in the late 2020s is a remarkable run. Most fields of science do not progress this fast. Plate tectonics, from its first proposal by Alfred Wegener in 1912 to its broad acceptance in the 1960s, took 50 years. The germ theory of disease, from Pasteur's first careful experiments to broad medical acceptance, took more than 30 years. Modern exoplanet astronomy is, in this respect, an unusually fast-moving field. The instruments, the techniques, and the talent are all converging on the questions in a way that previous generations of astronomical questions did not enjoy. The constellation Aquarius is in the autumn sky in the northern hemisphere between Capricornus and Pisces. It is one of the dimmer constellations in the zodiac. The Greeks associated the constellation with Ganymede, the most beautiful young man in their mythology, who was carried off to Olympus by Zeus to serve as cupbearer to the gods. The Babylonians, much earlier, associated the same patch of sky with the god Ea, who was the god of fresh water and wisdom. The Egyptians associated it with the annual flooding of the Nile, which was, by their calendar, governed by the rising of certain constellations. Almost every civilization that watched the sky carefully built a story around this small, dim cluster, often involving water in some form, perhaps because the constellation was traditionally seen during certain rainy seasons. Its brightest stars are not particularly bright. and the overall pattern is, by the standards of the more dramatic winter and summer constellations, not very memorable. TRAPPIST-1 is somewhere in that pattern, far too dim to see with the naked eye. To find it, you would need a serious telescope, careful coordinates, and a patient evening. Most amateur astronomers will never see it, but the system is there. Around that small dim red star, every 6 days, a small Earth-sized world is making its lap of its sun in its tidally locked configuration with its permanent reddish twilight. With whatever atmosphere it has, with whatever surface conditions exist, the planet is too small and too dim to see from Earth without specialized instruments. But the planet is there. Its day side is, at this moment, illuminated by the dim red glow of TRAPPIST-1. Its night side is, at this moment, dark. Its atmosphere, if it has one, is, at this moment, doing whatever thin atmosphere does on a tidally locked planet around a flaring red dwarf. We thought, briefly in 2017, that we had found 7 candidates for another Earth. We have, in the years since, narrowed the picture. 3 of the 7 are too hot. 2 are too cold. 1, TRAPPIST-1e, is right in the middle, with the most favourable conditions for surface liquid water. That one, the centre of the 7, the small middle planet of an obscure system around an obscure star, is the best chance we have at finding another Earth. There is a final thought worth holding on to before we close, which is about the slow nature of preparation in this kind of work. The TRAPPIST telescope, which discovered the system, started observing in 2010. The Spitzer Space Telescope, which confirmed the system's 7 planets, started operating in 2003. The James Webb Space Telescope, which is currently characterizing the planet's atmospheres, was first proposed in 1996. The whole instrumental chain that has produced our current picture of TRAPPIST-1 was being designed and built across decades. Most of the people who designed JWST were not the same as the people who designed Spitzer. The people who designed Spitzer were not, in many cases, the same as the people who designed Hubble. Each generation of instruments was, in some sense, a relay handoff. The previous generation built what they could. The next generation took it further. The current generation is using JWST to do what Spitzer could not, and the next generation will use Ariel and the ELT to do what JWST cannot. That continuous handoff across generations of scientists is one of the deeper structures of modern astronomy. Nobody in this field finishes the work. Everybody contributes a chapter. The book, if there is a book, is being written by thousands of contributors over centuries. It is the kind of long collaborative endeavour that on a smaller scale has built the great human institutions of the past, the cathedrals, the universities, the accumulated infrastructure of human knowledge. Modern astronomy is, in some real sense, one of those institutions just at the cosmic scale. There is one more thought I want to leave you with before sleep. The work of finding and characterizing other Earth-like worlds is, by any reasonable accounting, one of the more important things our species is doing right now. It is not the kind of work that produces immediate practical applications. It does not, in any direct way, feed people or build industries or solve geopolitical problems, but it is the work that, in the long run, will determine how we understand our own place in the universe. The question of whether we are alone or whether the conditions that produced us are reproduced elsewhere is one of the oldest questions our species has asked. It is, finally, becoming a question that careful observations can answer. The astronomers who are doing this work on the small dim red star in Aquarius are part of an answer that has been waiting for us in the photons of distant starlight for as long as there has been a galaxy. You can let the planet go for tonight. The work of finding out whether it is habitable is being done slowly by people you will never meet, on instruments you will never see, on a time scale that runs longer than your own. The next decade of observations will refine the picture. The decade after that will probably settle the question. By the time the answer is in, most of us listening tonight will not be alive to read it, but the answer will be in eventually. The patience of the work guarantees that. Good night. Sleep well. The little red star is still doing its slow, patient work in the constellation of Aquarius, 40 light years from where you are listening. The 7 planets are still in their resonant orbits. TRAPPIST-1e is still making its 6-day lap, with its permanent red twilight, with its uncertain atmosphere, with its possible ocean of liquid water, and its possible chemistry of slow life. The story is exactly tonight, at the place where we left it. The light continues to arrive. We continue to listen. The picture, one observation at a time, gets a little sharper. There is, somewhere in Aquarius, a small dim star around which 7 Earth-sized worlds are doing their slow, patient work. The star itself is too faint to see with the naked eye. The planets are too small to see with any telescope on Earth. Everything we know about them comes from the careful analysis of starlight, modulated by the planet's transits, accumulated over years, processed by software, and slowly assembled into a picture. The picture, by the standards of pre-exoplanet astronomy, is incredibly detailed. By the standards of where we will be in 20 years, it is the early sketch. The fourth of those worlds, the small middle one, the one we are watching most carefully, is sitting in the part of its star's neighbourhood where, given the right atmosphere, life, as we understand it, could exist. Whether it does, we do not yet know. Whether it could, we are still working out. The story is, by every measurement, the most quietly important exoplanet story of our generation. Good night, again. Sleep gently. The planet is still there. The small red light continues its slow burn. The 7 worlds continue their resonant dance. The story continues on the timescales of cosmic patience, regardless of whether anybody on Earth is watching tonight. The light from TRAPPIST-1 reaching Earth tonight left that star around the year 1985. 40 years of travel through empty space, carrying the small information about transits and atmospheres and stellar flares, finally arriving at our instruments tonight. The light, leaving TRAPPIST-1 right now, will not arrive on Earth until 2066. The next generation who will receive that light will be reading it on instruments we have not yet built. The data they will pull from those photons will be more detailed than anything we can pull tonight. The picture they will assemble of TRAPPIST-1e in their generation will be more complete than the picture we have in ours. We are, in this kind of work, custodians of a slow, patient observation that has been ongoing for 40 years and will continue for many decades more. The work passes from hand to hand. The instruments improve. The pictures sharpen. The eventual answer, when it comes, will be received by people we will not meet, on instruments we will not see, on a clock that runs longer than any of us. That is enough for tonight. Sleep well.